Good evening, gents. Welcome to our first video on trigonometry. By the end of this lesson, you should understand the basic concepts of trigonometry, what trigonometry means and how it relates to similarity and right-angled triangles. What I want you to focus on for now is just look at this triangle here. It's a right-angled triangle, as you can see. It has a base of 6.06 units, a height of 3.5 and a hypotenuse of 7. At the moment the angle down there is 30, and we're going to use the Greek letter theta to represent the angle that we're looking at down here, which at the moment, as I said, is 30 degrees. The first thing we need to be able to do is label the sides according to the angle that we're looking at. On a right angled triangle, the side opposite the right angle is called the hypotenuse. For this triangle, we're looking at the angle of 30 degrees. The side opposite the 30-degree angle is called the opposite side. And the side next to it, another word for next to, is adjacent. So that side is called the adjacent side. I want you to look now at the length of the opposite side to this angle and the hypotenuse. At the moment it's 3.5 units, might be centimeters, might be meters. At the moment it's 3.5 units, and the hypotenuse has a length of 7. If we write that as a fraction, we have opposite over hypotenuse equals 3.5 over 7, which equals a half. In other words, the opposite side is half as long as the hypotenuse. Now watch what happens when I make the triangle bigger. Notice that the angle doesn't change size. I'm going to make the triangle bigger without changing the size of this angle 30. So let's make that opposite side grow to, let's say, 5 units. Notice, when the angle is still 30, the opposite side is now 5, the hypotenuse is 10, but the ratio of the opposite side to the hypotenuse is still 5 over 10, which is a half. Here's a key connection between similarity and trigonometry. This triangle here is similar to the triangle we had before, which had an opposite side of 3.5 and a hypotenuse of 7. How do we know they're similar? Well, the angles are the same. We've got a right angle, a 30-degree angle, and this angle therefore must be 60. If I don't change the size of that 30-degree angle or the right angle, then we must have two similar triangles, and noticing, importantly, that the ratio of their sides don't change. The 5 and the 10, this opposite side is half as long as the hypotenuse, no matter how big the triangle is. See how the ratio doesn't change. No matter how big or small I make the triangle, this opposite over hypotenuse, the fraction, the ratio, is always 0.5 or a half. Now this is true of any triangle that has a 30-degree angle. You could say that for any 30-degree angle, the ratio of opposite over hypotenuse is always equal to a half. Let's have a look at another pair of sides. Let's take the opposite side and the adjacent side. At the moment the opposite is 3.46 and the adjacent is 6 units long, which gives us a ratio of 0.58, and that's a particular number which we'll worry about later. But the key thing is that if I, again, make the triangle bigger and smaller, that ratio of opposite over adjacent equals 0.58 doesn't change the whole time. No matter how big or small the triangle gets, these are all similar triangles that have the same size angle, and so the ratio of opposite over adjacent is always, for the angle 30 degrees, it's always 0.58. The question to think about now is what's going to happen if I make the angle bigger? The base stays as 6. What happens if the angle gets bigger? Well, hopefully you can see the opposite side is going to get longer. Let's have a look. If the angle gets bigger and the base stays the same, the opposite side has to get longer, and therefore, given that the adjacent side is the same and the opposite side is getting longer, watch how the ratio gets bigger. Here's the next question. For what angle will the ratio of opposite over adjacent equal 1? Think about what that means. Opposite over adjacent equals 1. That means the opposite and the adjacent are equal to each other. It was 6 over 6, for example. What angle will I need for that? Hopefully you can see, if that's 6 and that's 6, that makes this an isosceles triangle, which means that must be 45 degrees. 90, 45 and 45 make 180. So if they are both 6, they have an opposite over adjacent. The ratio there is 1, and therefore the angle is 45. Which means any angle bigger than 45, the opposite over adjacent ratio is bigger than 1. And any angle less than 45, the opposite over adjacent ratio is less than 1, until it gets essentially to 0. You haven't got a triangle anymore. My next question is, what is the biggest number that this ratio can be? Well, essentially it will be as big as you like. It can go on to infinity. There's a certain limit when you get to 89.999 degrees, and you've got essentially two vertical lines that are almost parallel but not quite, and it will get bigger and bigger and bigger as close to 90 as you get. Let's go back for a second to the opposite over hypotenuse ratio. Opposite over hypotenuse. What's the smallest that this ratio can be? And how will I make this ratio smaller? Well, hopefully you can see that opposite is on top, so if I make the opposite side shorter, this ratio will become smaller. And to do that, to make the opposite side shorter, I'm going to make the angle smaller. Until again, if the opposite side is almost 0, that will mean the ratio is almost 0, and the angle is almost 0. As this angle gets bigger, closer to 90, look at what happens to these two numbers as I make the angle bigger. They're getting closer and closer together because the lengths of the lines are becoming closer to the same length. So if I approach 90 degrees, this ratio here will be almost 1. It's not exactly 1, it's rounded off to 1, but it's approaching 1. It can never be 1 because if they're the same length, you haven't got a triangle. Now there's one final pair of sides to consider, and that's adjacent and hypotenuse. So adjacent down here at the moment is 6, and hypotenuse is 6.93. You can see this number here again has a strange decimal. It does have a meaning to it, which we'll talk about later. Notice when I change the size of the triangle, again this ratio 0.87 will stay the same. No matter how big or small the triangle is, as long as the triangles are similar, the ratio of adjacent and hypotenuse is the same. Now this one is slightly different. If I make the angle smaller, what's going to happen to this ratio? What's going to happen to these lengths in comparison with each other? The adjacent is currently shorter than the hypotenuse, and it always will be. But as I make the angle smaller, the hypotenuse is going to become smaller. And so this ratio, as the angle gets smaller, is actually getting bigger until it approaches 1. If I make the angle bigger, the hypotenuse is getting much longer than the adjacent, and so the ratio is getting smaller until it approaches 0. This hypotenuse is much longer than this adjacent side here.